Hello everyone. In this bite-sized video, I want to introduce amplitude modulation, which is a type of analog modulation scheme used in communication systems. Early communication systems were analog, for example AM radio and FM radio. These days, even broadcast radio is going digital, mainly due to regulations. The analog message signal, or information signal, that we want to transmit will be denoted as m of t. We assume that m of t is a low-pass signal with bandwidth w. The magnitude of the Fourier transform of m of t, which is denoted by m of f, is shown here. We also assume that m of t is a power-type signal, which means that the signal has finite power, as shown here. Note that a power-type signal has infinite energy. To send a message signal m of t, we are going to modulate a carrier signal c of t. The carrier is shown here as c of t equals ac cosine of 2 pi fct plus phi c. Here ac is the amplitude of the carrier signal, and fc and phi c are the frequency and phase of the carrier signal. What we mean by modulating a carrier is that the information signal is encoded in some characteristic of the carrier signal. When the information signal is encoded in the amplitude of the carrier, we have amplitude modulation. This is called AM. When the information signal affects the frequency of the carrier, we have frequency modulation. This is called FM. When the information signal affects the phase of the carrier, we have phase modulation. This is called PM. Frequency modulation and phase modulation are examples of angle modulation, which we will study after amplitude modulation. As I noted before, in analog modulation, we typically use a carrier signal. This was the signal called c of t, which is a sinusoidal signal at a certain given frequency, called the carrier frequency. We will see that the act of modulating with a carrier signal has the effect of translating the frequency spectrum of the transmitted signal up to the frequency of the carrier signal. So, why do we modulate a carrier signal, instead of just transmitting the message signal directly? There are several reasons for this, as is described here. First, modulating a carrier allows us to have simultaneous transmissions from different sources by simply having them transmit at different carrier frequencies. Second, since the antenna size is on the order of the signal wavelength, we need big antennas at low frequencies, and hence we can have smaller antennas at higher frequencies. Typically, the carrier frequency is much higher than the message bandwidth. Third, the channel may have a usable frequency band, so modulating to a carrier allows us to translate the signal into the usable pass band of the channel. Finally, expanding the signal bandwidth gives us immunity to noise. Keep in mind that, because of these advantages, modern digital communication systems also modulate using a carrier signal, with a high carrier frequency. For example, when we talk about Wi-Fi at 2.4 GHz, or 5 GHz, we are actually talking about the carrier frequency. Recall that, when the message signal, m of t, changes the amplitude of the carrier, we call it amplitude modulation. There are a couple of ways of implementing amplitude modulation. We can use double sideband suppressed carrier AM, and variants of it such as single sideband AM, and vestigial sideband AM. These are phase coherent modulation schemes. We also have conventional AM, also called double sideband with carrier. This is a phase non-coherent modulation scheme. In double sideband suppressed carrier AM, the modulated signal u of t is the message signal m of t multiplied by the carrier c of t. In other words, the information signal is encoded in the amplitude of the carrier signal, so this is amplitude modulation. The carrier is a sinusoidal signal, and we typically write it as a cosine function, namely ac cosine of 2 pi fct plus phi c. Here we show the magnitude of the Fourier transforms of the various signals. First, here is the Fourier transform of the message signal m of t. This Fourier transform is denoted by m of f. The Fourier transform is in general a complex number, so we plot its magnitude and phase. Below that is the Fourier transform of the modulated signal u of t. Note that the modulated signal u of t is the product of m of t and c of t. From Fourier transform theory, we know that multiplication in time is convolution in frequency. The Fourier transform of m of t is m of f. The Fourier transform of cosine of 2 pi fct is two delta functions at frequency plus minus fc. So the Fourier transform of u of t is the convolution of m of f and two delta functions. This is a frequency domain view of double sideband suppressed carrier AM. Here are the analytical expressions for the modulated signal. In the time domain, we have u of t. In the frequency domain, we have u of f. Looking at the Fourier transform of double sideband suppressed carrier AM, again, we see that the Fourier transform is non-zero for only part of the spectrum, namely from fc-w to fc plus w. So, we say that the double sideband suppressed carrier AM signal has bandwidth of 2w, which is twice that of the message signal bandwidth, which is w. Hence, we use the term double sideband. Also, from the Fourier transform of u of t, we see there is no delta function at plus minus fc. In other words, the carrier is suppressed and is not explicitly transmitted. This is why this scheme is called double sideband suppressed carrier AM. So, how do we demodulate double sideband suppressed carrier AM? The transmitted signal is the modulated signal u of t. At the receiver, we have the received signal r of t, which is just the transmitted signal plus noise. We want to extract the message signal m of t from the noisy received signal r of t. Let's look at the noiseless case first. Here r of t is just u of t. We first multiply r of t by a locally generated version of the carrier signal to get the signal z of t. Note that the locally generated carrier signal has frequency fc, which is known by the receiver, and phase phi. Keep in mind that the carrier phase is phi c, which is different from phi. Expanding this and using trigonometric identities, we get that z of t is a scaled version of m of t. This is good, but the scaling factor matters. The 1/2 AC term is just a constant, so we can ignore it. However, the other scaling factor cosine of phi c minus phi cannot be ignored. If phi equals phi c, then cosine of 0 equals 1, and we have good recovery of m of t. However, if, say for example, phi c minus phi equals pi over 2 radians, then cosine of pi over 2 equals 0, and we have no signal. The takeaway is that if the receiver has knowledge of both the frequency and phase of the carrier, it can perfectly recover the message m of t. This is known as phase coherent demodulation, because the assumption is that the receiver knows the carrier phase. In practice, the receiver has to estimate the carrier phase. Estimating the frequency and phase of the carrier is known as synchronization. This is typically done via a circuit called the phase-locked loop, or PLL for short. We will discuss the phase-locked loop later when we study frequency modulation. Now, recall that, the double sideband suppressed carrier AM signal has twice the bandwidth of the message signal. This seems like overkill, and we want to know whether we can get away with using less bandwidth. The answer is yes. We can use single sideband SSB or vestigial sideband VSB modulation. Let's look carefully at the Fourier transform u of f of the double sideband suppressed carrier AM signal. The upper sideband is the part of the spectrum where the frequency has magnitude greater than fc. And the lower sideband is the part of the spectrum where the frequency has magnitude less than fc. It turns out that the upper sideband, or the lower sideband, contains all the information about u of f, and hence about m of f. This motivates us to transform double sideband into single sideband by filtering out one of the sidebands. If our filtering is not perfect, we get vestigial sideband. We will see later that double sideband suppressed carrier, single sideband, and vestigial sideband can all be demodulated using the phase coherent demodulator we just studied. Let's take a closer look at single sideband modulation. Since either the lower or upper sidebands contain all the information about the message signal, we can simply transmit just the single sideband. We first see m of f, the magnitude of the Fourier transform of the message signal, which has bandwidth equal to w. Next is the Fourier transform of the double sideband suppressed carrier AM signal, which has bandwidth equal to 2w. Then we see the Fourier transforms of the upper single sideband signal and the lower single sideband signal, both of which have bandwidth equal to W. Now, let me show you how we can unify double sideband suppressed carrier, single sideband, and vestigial sideband. We discuss generation of such signals first. The strategy is to use bandpass filtering of a double sideband suppressed carrier AM signal. At the top is a block diagram showing how to generate single sideband AM and vestigial sideband AM using this approach. At the transmitter, the message M of t is multiplied by the carrier C of t and then passed through a bandpass filter H of f to get the modulated signal to be transmitted U of t. Depending on the form of the filter H of f, we can get double sideband suppressed carrier AM or single sideband AM or vestigial sideband AM. In Figure 1, when H of f is a bandpass filter of bandwidth 2W centered at frequency Fc, we get double sideband suppressed carrier AM. In Figure 2, when H of f is a bandpass filter of bandwidth W and passes only one sideband, either the upper or lower sideband, we get single sideband AM. Note that single sideband AM requires ideal filters with perfectly sharp cutoffs. In Figure 3, when we have non-ideal filters, we get vestigial sidebands. The root of the word vestigial is vestige, which means traces, meaning that traces of the other sideband remain. So, when H of f is a bandpass filter of approximate bandwidth W and mostly passes only one sideband, either the upper or lower sideband, we get vestigial sideband AM. Vestigial sideband typically has a bandwidth of 1.25 W, so we see that it is a compromise between double sideband suppressed carrier and single sideband. It is interesting to note that vestigial sideband modulation was used in analog television. These days, most of our television broadcasts are digital. Let's move on to the demodulation of double sideband suppressed carrier, single sideband, and vestigial sideband. The good news is that we can use the phase coherent demodulator we discussed previously. At the top, we have a unified block diagram of the phase coherent demodulator. The received signal R of t is first multiplied by a locally generated version of the carrier. In the phase coherent demodulator, the receiver has to synchronize with the phase of the received signal. As mentioned before, this is typically done via the phase-locked loop, or PLL. The multiplication by the local carrier shifts the spectrum to baseband around 0 Hz. To recover the message, the signal is then put through a low-pass filter of bandwidth W. Note that this works for double sideband suppressed carrier signals, single sideband signals, and vestigial sideband signals. Here is an example with single sideband. Figure 1 is the frequency spectrum of the modulated signal. Note that this is upper single sideband. Figure 2 is the frequency spectrum of the shifted signal, after multiplication by the local phase coherent carrier. Figure 3 is the frequency spectrum of the low-pass filtered baseband signal. This is the recovered message signal M of f. Alright, this brings us to the end of this bite-sized video on phase coherent amplitude modulation. Thank you.